So today we will start a new module, which is our last module before exam, before the midterm exam. From our previous meeting, we already talked about surface runoff. And for today's module, it is still related to the surface runoff. But in this duration curve and mass curve, it is more likely related to the reservoir of the water. So regarding the surface runoff, it is related to the availability of water, which means the amount of water or discharge which is estimated to exist in a location, for example, in a weirs or other water structures, in a river with certain amount and within a certain period of time. And of course, the availability of this water, it has a strong connection to the water consumption or water demand. This water consumption is the amount of water needed. The kind of the consumption are varied. Here an example such as water consumption for irrigation, for domestic water, for drinking water and household water, and then non-domestic such as for the trade, office, and the industry, and for the river maintenance, for farming, fishery, and hydroelectric power plant or pembangkit listrik tenaga air. So this variation of water consumption can make water demand also different on each location. It is related to the availability of the water. So the amount of the water available have to be enough to give the demand of this water consumption. For the water availability, it is varied all the time depending on the season. As you already know, in dry season, of course, there are less water available than in the rainy season, especially related to the surface runoff. There are also a type of river that we already talked about on our previous meeting. There are types of river which has no water in the dry season. There are also types of river which has water in the every season, and there are also type of river which has only water in the rainy season. Regarding the water demand, this water consumption or water needs are always certain and sometimes even tend to increase, especially related to the drinking water or for the household purposes. It tends to increase as well as the increasing of the population. So if the population increasing, of course, the water needs or water demands are also increasing. And related to the surface runoff, the availability of the surface water flows will be utilized optimally to meet existing needs. That's why we need to study this mass curve and duration curve to know how to utilize them optimally. First, we talk about the duration curve. It's also called flow duration curve because it is a flow curve. Previously, we already talked about hydrographs. So the hydrographs, it is a curve which shows the relationship between the discharge and the height of the water. And flow data curve such as hydrograph shows when the amount of discharge in a river flow occurs. For example, here the discharge is on the y-axis, and on the x-axis there is a date of the event. The amount of discharge may occur repeatedly or only a few times, or it may be only once. So from this graph, we can see that the average daily discharge of 100 occurs in like this one first time, the second time here, and then third time here, and then this one is the fourth time. So this amount of discharge occur repeatedly in particular dates. So this flow duration curve or duration curve is a graph showing the frequency of river discharge during a certain period of time within a specified period of observation expressed as percentage of the occurrence time. So the right one, this is the duration curve. For example, here we have like discharge of minimum, and this is the dependable discharge, or in Indonesia we call it debit andalan, and here is the maximum discharge. And for the x-axis, there are percent of time indicated flow was equal or exceeded. This one is the percent of time of the maximum discharge happening. Of course, it will be low percentage of time because it doesn't happen like repeatedly, only maybe 1 or 2 times. And then this one in this dependable discharge, here we have like this percentage of time, approximately like 30% maybe, because the location is here. And then we have the minimum discharge. It has to be 100% occurrence, because this one is the minimum. So it has to be happen all the time, because before it reach maximum, of course it will reach minimum first. Before it reach the dependable discharge, of course it will reach minimum first. So this percentage of time indicated the flow was equal or exceeded. So it can be equal to minimum discharge, or it can also be more than the minimum discharge. That's why the percentage of time would be 100%. To make it more clear, this is another example from this figure. This is the figure of flow duration curve, another one, different but similar. From this figure, we have like the A meter cube per second, B meter cube per second in this y-axis. And then in the x-axis, we have 50% and 100% of probability. From this figure, we can see that the discharge of the A meter cube per second, occur during the observation period with the probabilities of 100%. So this A meter cube per second can be concluded as the minimum discharge. If the observation period is 1 year, then throughout the year, the A meter cube per second always occur. So if this debit is used as water demand throughout the years of 12 months, this A meter cube per second amount of discharge must be fulfilled. So if the demand is this big, of course it has to be fulfilled because it occurs in 100% possibilities. Means if the observation period is 1 year, it occurs every day. if the B meter cube per second discharge is used as the water demands, the needs can only be met for half a year, while the remaining half a year cannot be fulfilled. Which means here we have like B meter cube per second with the probability of 50%. So in the other 50%, the discharge is not more than this B meter cube per second. That's why we have like only 50% probabilities, because the other 50%, the discharge will be less than this B meter cube per second. If we observe this curve during the half-year period in which the demand discharge can be met, there are also times when the discharge are greater than B meter cube per second are not utilized as a whole, meaning that only B meter cube per second is tapped and discharged. So here we have like in this curve, the discharge happen more than B meter cube per second is happened in 50% probabilities, while the demand is only B meter cube per second. So the rest is not utilized, and then the water which is utilized is only until this B meter cube per second in this 50% period of time in a year. And then another example regarding the type of the river. So we already talked about perennial river, intermittent river, and ephemeral rivers in our first meeting. No, not first meeting, previous meeting. And this graph shows this is the flow duration curve regarding these three types of the river. The daily discharge with the percentage of probability. As you already know, the perennial river, it has water in every season. So the discharge will not be zero, because even in the dry season, there are water in this type of river. It is different with this intermittent and ephemeral rivers, which only has discharge when it's raining or when it's in the rainy season. That's why there is zero discharge in this type of the river. In a perennial river, the percentage probability of 100% discharge is a value, it's a finite value. On the other hand, in an intermittent or ephemeral river, the stream flow is zero for a finite part of the year, and such K100 is equal to zero, which means there are times in this type of river, intermittent and ephemeral river, where the river has zero discharge or has no water in the system. But in this perennial river, there are no times in this river in 1 year, for example, without discharge or without water in the system. So here we have a flow duration curve of the perennial river. We can see in the percentage probability of 100%, there is a very small discharge here, like approximately maybe 30 meter cube per second. While in the intermittent and ephemeral rivers, there is no 100% probability. The zero amount of the discharge would be in 70% probability, because there are no discharge that will always happen in this certain period of time. So for this intermittent and ephemeral rivers, there are times approximately 30% probability where the discharge is 0, where the river doesn't have any water in the system. So what is the relationship between this dependable flow with the reservoir? Here we have a curve from before, like this is the curve similar to this one, but here we have like this QD or dependable flow, or in Indonesia we call it debit andalan. And when the QD happened, the water which is utilized is only this big. So the water more than this dependable discharge will not be utilized. That's why we need this reservoir. So the area under the duration curve shows the total volume of flow during the observation period. So this area below this curve, this duration curve, the area below is the total volume of the flow. It is similar when we calculate the total volume of our hydrograph. So it will be the same with this duration curve. So it is possible to hold a portion of the volume of the flow with the help of reservoir so that the required discharge can be adjusted as optimally as possible. Such a discharge is called the dependable flow. So if we have this dependable flow here, and then we have the duration curve right here. And of course, if we utilize this this peak, this dependable flow, and then we have the availability of the water in this duration curve. Of course, the water available here will not be utilized because we only utilize until this dependable flow. And where does this water go? We can store it in the reservoir. And after that, after we store it in the reservoir, the next time we need it, it is when we utilize this dependable flow, but the availability of the water is only in this peak. So we have like the deficit or the lack of the water here. And then we can use the water that we already stored previously on this time of period. So we don't have to have the water deficit, and then we can use the dependable flow properly. How about if we don't have a reservoir? It also can happen. So the dependable discharge is the minimum river discharge with a certain amount that has the possibility of being met, which can be used for various purposes. So without reservoir, for irrigation purposes, the minimum flow of river for the possibility of fulfillment is set as 80%, or depends on the cropping pattern, while for other water needs other than irrigation, it usually set as 90%. This is for the household water or drinking water. And this is the amount of dependable flow with various purposes. And it is calculated using the basic year method, which is determining a certain year as the basis for planning, while the probability analysis to determine the dependable flow is calculated by the Weibull method. So if you want to like estimate the dependable flow for drinking water, it should be like 99%. And for industrial water, it should be 95 until 98%. For irrigation, if the area is humid, 70 until 85% should be enough. And for the dry area, 80 until 95%. And for the hydropower plant, 85 until 90%. So the bigger the percentage of the dependable flow, the lower the discharge. Because if it is like 100% dependable flow, which means it should happen all the time during the period of time. For example, in 1 year, it should be happen like in 365 days. So if this drinking water has lower dependable flow than 99%, it means that in 1 year there are days which this flow is not met. So it will be problem because if this drinking water has like a deficit volume, it should be it will give bad impacts in the population health. So it should be like at least 99% fulfilled. For the irrigation, it will be different because it doesn't has to be like that all the time. As you know, the cropping pattern is not the irrigation area is not used in the full in 1 year. So there are times that we don't use this irrigation area. There are times we plant this irrigation area with plants. There are also times this irrigation area has no plants. That's why for this irrigation water, the probability of dependable flow is not as high as drinking water or industrial water. And how to make a duration curve? So from the data available, we can make it by first arrange in an ascending order of discharge. For example, actually this is already simplified. The original example is not this simple, but if you want to know more about this, how to make a duration curve, you can see for the original example, like before it became like this, we have to like calculate this daily discharge based on the days, like how many days this daily discharge pass, or how many days has more than this amount of daily discharge. At first, we have to calculate the event first, and then we cumulate the events, the total events, and then we calculate the percentage of the cumulative. So here, for example, oh yeah, you can also see another example in the ebook, the ebook that I already shared in the My ITS classroom on our, as I remember, it's our first meeting. It's an ebook titled Engineering Hydrology. There are also another example of how to make a duration curve there. So here we have like the daily discharge of 5 meter cube per second, and then 10 meter cube per second, 15 meter cube per second, until the biggest one is 50 meter cube per second. And then for 1 year, we calculate the events of this daily discharge happened. For example, here we have in the daily discharge of 5 meter cube per second happened in 22 events, or maybe we call it 22 days. So in this year, there are 22 days which has daily discharge of 5 meter cube per second. In this case, maybe this is a river. And then there are also 46 events for this 10 meter cube per second daily discharge, etc., until it become the total of 365 events, which means the time period is in 1 year. And after that, we calculate the cumulative events. And from here, we can conclude that the smallest discharge would be the discharge that always happens. So, for example, even though the discharge is 50 meter cube per second one day, before it reach 50, it has to reach like 5, 10, 15, 20, etc. That's why the total event of 5 meter cube per second of daily discharge would be every day in a year. So it means it would be 365 events. And after that, we calculate again for the daily discharge of 10 meter cube per second, how many total events that we will have. Here we have the events of 10 meter cube per second daily discharge is 46 events. But because of this daily discharge happened, of course, we cannot accumulate the discharge with a smaller value than this one. That's why we need to calculate it without this 22 events of 5 meter cube per second. I hope you can understand my explanation. So that this 10 meter cube per second, the total cumulative events is 343 events, which means in 1 year there are 343 events which has daily discharge of 10 or more than 10 meter cube per second. That's why we didn't calculate it the 5 meter cube per second daily discharge, because in 5 meter cube per second daily discharge, it doesn't it is not more than 10 meter cube per second daily discharge. So it doesn't happen in this 22 days of event. So for 10 meter cube per second, it's only happened in 343 total events. And then we calculate for 15 meter cube per second using these 343 events minus this, wait. Yeah, 343 events minus this 46 events. And here, because we cannot calculate the discharge of 10 meter cube per second, because in 15 meter cube per second, the minimum discharge is this 15 meter cube per second, so that these 5 and 10 will not be included in this total events. And then we calculated until the last one, we have like 50 meter cube per second of daily discharge. In 1 year, there are only 5 days, which has this amount of discharge. Of course, the total events will be only 5 days, because this is the 19 minus the 14 events. And to draw the duration curve, we need to calculate the percentage cumulative of probability. So it doesn't stop until this total events, but it will still continue until we get the percentage cumulative of probability. Of course, if the total events is 365 in 1 year, the percentage of probability is 100%. And then for the second one, 343, the percentage probability in 1 year is 343 divided by 365 equal to 94%. And so on until the last one, we have like 5 total events in 1 year, which means the probability is only like 5 divided by 365, which means 1.4 percentage of probability. So after we got this percentage of cumulative, we got this daily discharge from the data, we can plot the duration curve. From this curve, we can know that this 5 meter cube per second happens every day in 1 year because it has 100 probability. And for the minimum discharge of, the minimum percentage of probability, this is the maximum daily discharge of 50 meter cube per second, which has like only 1.4 percentage of probability, which means in 1 year it only happens like for 5 days. That's it for the duration curve. So the purposes of this duration curve is to know the frequency of the amount of the discharge happen, which can be also utilized to know or to estimate the amount of the dependable discharge based on the purposes. So we now move to the mass curve. So this flow mass curve is quite different with this duration curve, because in the duration curve, we use discharge as the y-axis, but in the mass curve, because of its name, the mass, of course, we have to use the volume of the flow. So we use volume as the y-axis and time as the x-axis. The flow mass curve shows the relationship between the time and the cumulative volume of the flow. So for the previous one, the duration curve, we have like cumulative of the percentage of probability. But here we have the cumulative of the volume of the flow. This flow mass curve provides an overview of the amount of water flowing in the river, but not the discharge, but the amount of the volume of the water flowing in the river. So here we have an example of like the discharge of the water in the river in the certain period of time. For example, in the table, we have the data until like 5 hours. So in the first hours, the discharge is at start, the discharge is 4 meter cube per second. And then for until the first hour, the discharge increasing to be 10 meter cube per second, and then increasing again to be 15 and 25, and then decreasing to 10, and then increasing again to 18. From this discharge, we can calculate the volume. Because of the discharge units of meter cube per second, of course, if we want to calculate the volume, we have to multiply it with time. Here we have time units of hour, so we have to multiply it with 3,600 seconds, and then we can get the volume of the flow on each time step. So the steps doesn't stop here. So after we got the volume of the water flowing on each time steps, like on the first hour, the volume is 25.2. The second hour, the volume is 45. This is because of the discharge on each hour. And if we want to make a mass curve, we have to accumulate the volume to be the volume cumulative. So for this volume cumulative, we have to add the volume on each time steps with the volume from the previous time steps. For example, here we have, in the time step of 1 hour, we have to calculate the time step of 1 hour plus the 0 hour. And then after that, we have cumulative volume of the second hour. We have to calculate the volume in second hour plus the volume in the previous hour, which is in the first hour. And we do it until it reach like the last time steps. It will be the biggest volume cumulative, and the shape of the curve will be increasing because of each time step the water is coming in. It doesn't always like this, because sometimes the water is not always coming in, but there are also the water which is coming out. So this mass curve can also be used to draw the amount of water coming out from the particular water bodies. For example, if we use pump, of course the discharge will be constant. For example, if we use like pump 1 meter cube per second, the Q here will be always 1 because we use pump, so it has like a constant discharge. And then we can calculate the volume of the water which is going out because of this pump, and then or the water coming in from the pump can also be calculated. So it depends on the occasion. And then we can also calculate the cumulative of the volume of the water from the pump. So this mass curve can also be used as an outflow mass curve, but it also can be used as an inflow mass curve. So it doesn't always has to be the inflow, but it also can be used as an outflow. This is the example of the curve between water demand, water availability, and water use. The first one, the water availability, blue one. This is the mass curve value of the inflow or the water available. And then there is this water demand line as a red color. It shows the mass curve of requirement water or the water required or the water needs. And then there is this green line, the water usage. This is the mass curve comparison, which is the same as demand line compared to mass flow curve or mass inflow. So this water usage. It's actually the same with the water demand, but it's firstly compared to the water availability. So if the demand is bigger than the available water, of course the usage can be bigger than the available water. That's why we need to draw the water usage to know whether the demand is met or not, whether the water available is sufficient or not to give the amount of the water demand required. Here we have the available water of blue line, and then we have the demand of the red line. As we can see here, the water demand is bigger than the water available in this V1. And then here we have the water demand is lower than the water available. This is the V3. This is where the reservoir can be used. For example, if we want to use this reservoir in the beginning, we cannot use it because it hasn't it doesn't have like amount yet, and so we have to draw the water usage in the green area, in the green line, because here we have like a demand that cannot be met. But here we have like the water available here, this amount of water available. Of course, we can only use the water as big as the water available. That's why we start to use the water here, and depends on the demand. Here we have, then we throw it with the starting point. Depends on this inflow curve of the water available. And then after that, we calculate, we draw again the water usage in green depends on the water demand in the red line. So the water that we use, actually the amount is the, it depends on this water available, but the curve is the same with the water demand. The reservoir capacity here, so from this curve, we can know that the water here has like a lack of water, but here we have like a surplus of water. So this one is deficit, this one is surplus. In this surplus area, because the water available is not used yet, it's not all the water available is used. That's why we can use the reservoir to store the water, so that the water can be used later or in the future where the water demand is higher than the available water. This reservoir capacity, it can be used as the water storage when there are surplus discharge, and it can also provide more water when there are deficit discharge. So the water, if there are deficit discharge, we can take the water from the reservoir. But if there are surplus discharge, we can also store the water to the reservoir. Reservoir capacity has to be enough to store maximum amount of surplus discharge. And then there are various types of reservoir purposes. So there are reservoir for irrigation, for drinking water, and then also for the flood control. This different reservoir has also different purposes. So for the first one, the reservoir for irrigation are usually also used as a reservoir for hydropower plants, because in hydropower plant, usually it is located in the mountainous area, as well as the irrigation also, because sometimes the water coming out from this reservoir, part of it can be used as an irrigation, part of it can be used as an hydropower. In this reservoir for irrigation and hydropower plants, the water in the rainy season exceeds the demand, so the water available is more than the water that we use. So the rest of the water which is not used can be stored in the reservoir for later use in the dry season. So for example, if in the dry season, if in the rainy season there are a lot of rain, and but the demand, the water demand, is the same in the rainy season and dry season, for example, and then the rest of the water can be stored in the reservoir, so that if in the dry season we have like deficit of water, we can get the water from the reservoir out, which we already stored in the rainy season. The second one, in a drinking water reservoir with a fixed inflow, if the consumers have used a little amount of water, for example at night, the rest of the water is stored in the reservoir to be used at peak demand or early in the afternoon. Which means in this reservoir for drinking water, if the inflow is fixed, for example, the inflow is constant, but the outflow is depends on the human activity. For example, at night, the humans are far asleep, so that they didn't use this drinking water reservoir too much. That's why there are water that has to be stored in the reservoir, so that it can be used if in the morning there are peak demand. And the third one, the flood control reservoir. The purpose of this flood control reservoir is to retain water when there is a big flow of water because of the rainfall, maybe, which can cause a flood, to secure the downstream river area. And then after the area is safe, it can be released when the inflow rate decreases. So, for example, there are big rainfall, and then this flood control reservoir will be stored the water from this big rainfall and retain it, so that the flow of the water in the reaching downstream will not be too much, will not be affected from the big rainfall. And after the rainfall stops, we can release the water from this reservoir, which we already stored before, and the water from the rainfall, we can flow it into the downstream of the river. So it will be safer for the downstream, and there will be no flood. And the reservoir storage itself has various allocation zones. Here is the example. The upper zone, the most upper zone is the surcharge storage. This is the top in the surcharge, which has various amount of water. So this is the usual zones, which has changed many times, depends on the reservoir activity. And then after that, we got this flood control zone. This is usually the water which is stored for controlling the flood. And then the third one, we have like conservation zone. This is most likely the water that has to be in the reservoir in the normal condition. So if there's no big rainfall, and then if there's no drought, the water which has to be in the reservoir is in this conservation zone, or the main zone. And the last one, the deepest zone of this reservoir storage is the dead storage. This is the water which has to be in the reservoir, the minimum of the water which has to be in the reservoir. For example, if there are very long dry season, there are drought, the reservoir have to be not dry. At least it has to be wet and contain at least this amount of water in the dead storage zone. Enough with the explanation. Now we move to the example so that we know how to use this curve properly. So for the duration curve, actually we use it for calculating the dependable discharge. But for the mass curve, we can use it to estimate the capacity of the reservoir, which we can use, which we needed to solve our problem. Here we have like two different methods of mass curve. The first method is the reservoir operation, and the second method is the S-curve method. For example, in this example one, there is a city which plans to provide clean water for its residents. And for this reason, a water pump with a capacity of 1 meter cube per second is used to work continuously for 1 full day. Calculate the reservoir capacity that must be prepared using reservoir operation method and S-curve method. So the inflow would be the water which is coming from the pump, and then the outflow would be the demand. Here we have the demand. The demand is from the data. The pump is from the pump which has like 1 meter cube per second capacity. And it works in 24 hours in 1 day. And then we can calculate first using reservoir operation method. From this later, you can see the differences between each method. So this first method is the reservoir operation method. In this reservoir operation method, you can calculate the differences between the demand and the water available. This is the water available in this case is from the pump, which has the capacity of 1 meter cube per second. And then it has this demand. And then we can calculate the differences between demand and the pump so that we know the total amount of this reservoir needed. So here, if the pump is bigger than the demand, it means that there are no water shortage. So we won't use the water from the reservoir. And if there are water shortage, for example, here the demand is bigger than the pump capacity, we need more water supply from the reservoir. That's why we calculated here the demand minus the pump is equal to this number. And then to know the volume of the reservoir that we needed, we have to calculate the total of these differences between the demand and the water available. And the key to this method is if you use these two methods, despite of the differences method, the results will be the same. So here we have the results of 13,478.4 meter cube of volume of the water in the reservoir that we need. to cover our water demand, which has bigger value than our pump capacity. How about if we use the S-curve method? To use the S-curve method, we have to calculate the cumulative discharge. For example, here we have the water demand and then the pump capacity, and then we have to accumulate the discharge of the demand and then of the water from the pump. After we accumulate them, we can calculate the differences between the water demand and the pump. This water demand and this pump, the differences would be minus if the pump is bigger than the water demand. So it means the water which is coming out from the pump is more than the water needed to than the water demanded or the water needs. It will be positive if the amount of the water needed is more than the water which is going out from the pump. So here, using the S-curve method, we can calculate the total volume of the reservoir that we needed by looking for the maximum differences and the minimum differences. So the maximum gap and the minimum gap, as in the maximum is the +1, is the volume where the water demand is less than the pump. Sorry, the water demand is more than the pump. And then the minimum is where the water demand is less than the pump. And after that, we can calculate the total by accumulating the maximum and the minimum value with the absolute minimum value. So it will not be negative, but it will be positive both. And then we got the same total with the one that we calculated earlier using this reservoir operation method. They're using two different methods, but getting the same results. We can conclude that these two methods has plus and minus. For example, and this reservoir operation, from the table we can see that it looks easier than the S-curve, like it looks simpler than the S-curve, because you don't have to calculate the cumulative volume. You only have to see the gap between the inflow and the outflow, and then you only have to write the deficit of the water. So the surplus, you don't have to write it. That's why we write 0 for the amount of the water which has no lack of water, and then we only draw the number of the differences when the water demand is bigger than the water from the pump. The second example, this is still regarding the capacity of the reservoir required, but here we use the other water demand and the other water required than the previous example. Here we have like 1 year of observation, and in the river there are the water available as big as here in the data. Oh, I think this data of available water is not correct. This is correct. Yeah, I will check it later. And then we have like this assumption of constanta of the evaporation pan is 0.7. As you already know, or maybe you still remember that we talked about evaporation pan on our previous, not the previous one, but the last few weeks. And this evaporation pan can calculate how much water evaporates to the sky or to the air, and then the percentage of erratic rainfall is 80%, which means the 80% of the rainfall become the surface runoff, and the 20% of the rainfall become infiltration, which is infiltrates to the groundwater. And then the inundation area is considered to be 1 hectare. This inundation area will be useful to calculate the amount of the evaporation and the amount of the rainfall based on the area. And in this month, we have water available, and then from this water available will be deducted because of there are evaporation, but it will be added because there is rain, and then the demand will be for irrigation and then for the downstream area. To calculate the contents of the reservoir from the amount of the water available, we have to calculate the available water minus the evaporation and add it with the rainfall. For example, we have the available water of 2,100 times 10 power with 3 meter cube, or here we have like 2,100,000 meter cube, and then minus with the evaporation 0.7 because of the evaporation pan. This is the amount of the evaporation, and then 10 power with 4 because of the area of 10 hectare. And then for the rainfall, we added the water from the rainfall because of the effective rainfall of 80%. We got this 0.8 times 90 millimeter of the water from the rainfall, and then times of the Indonesian area of 10 hectare. And then after calculating the water available, we have to calculate the total demand, which is the water for the irrigation and the water for the downstream area. Usually for the downstream area, it has to be the water for the population. For example, for the household, for the drinking water, etc. Sometimes for the fisheries also, if the population has like a pond or something like that. And after we calculate the water available and the total water demand, we can get this volume of reservoir required. So the total available water is the water available minus the water evaporates plus the water from the rainfall. And then the total water demand, it is for the irrigation and for the downstream population necessity. And from these two things here, the available and the demand, we have to calculate the demand minus the availability. So when the demand is bigger than the available water, it means that there is a lack of water, which means we have to take the water from the reservoir. Here we have 0 because we have more water available than the demand of the water. Here we also have 0. And then started from the May until the December, we have the lack of water with such amount. And then we can sum it into the total lack of water so that the volume of the reservoir needed in 1 year is this big to fulfill the water demand from this area. By seeing this graph, we can know, by seeing this table, we can know that they use reservoir operation method. And you can also calculate it using the S-curve method. And then after that, you can check it whether the results is the same or not with the other method. If the result is the same, you're correct. If the result is not the same, probably there is something wrong with the calculation process. So yeah, this one is to summarize the differences between reservoir operation and the S-curve method. For the reservoir operation, you only have to find the value of water shortage or the lack of water, which means the demand of the water minus the availability of the water. After that, you can calculate the total volume of the reservoir by adding the total amount of the water deficiency. And on the other side, the S-curve method, you have to find the respective cumulative values for water supply and demand. So for the S-curve, because of the name of this S-curve, you have to cumulate it so that the curve becomes similar to the S alphabet. And then after you cumulate it, you have to find the differences between the cumulative water availability and the cumulative water needs. And then the total volume would be the maximum differences plus the minimum differences, which means the maximum differences is when the cumulative differences is positive, and then the minimum differences is when the cumulative differences is negative. But here we have an absolute sign so that the negative become positive, so that the total volume will be maximum differences plus the minimum differences. I think that's it for today's material of the duration and mass curve. Should you have any question, feel free to ask.